Hello, folks. Today we're going to talk about the kinetic theory of gases. So, in this video, which is part 1, we're going to talk about monatomic gases. For example, helium. Now, each molecule of helium has just got one atom. Now, this atom of helium has got 2 protons and 2 electrons, and the 2 electrons are in a 1s orbital if it's in the ground state. If we ignore all this complicated internal structure, and if we represent helium atom as just a point particle, let's see how far we can take that. So let me start with a rectangular box. And in this box, we are going to place one atom of helium and represented by a point particle. Now this point particle is going to be buzzing around this box, bouncing against the walls. So we need to talk about its velocity, which means I need to set up a coordinate system. So what I'm going to do is take the direction along the length of the box as my x-axis. The width will lie along the y-axis and the height along the z-axis. Let's see what happens to this atom when it comes and collides against the walls. Remember the old problem of a tennis ball hitting a wall, colliding elastically and then bouncing off so that the angle of incidence equal to the angle of reflection? Keeping the same speed, there is no loss of speed because the collision is elastic. You will remember that the component of the velocity perpendicular to the wall gets reversed, whereas the component parallel to the wall doesn't change. When this atom comes and collides against this right side wall, the x component of the velocity gets reversed. The y component and the z component do not change, assuming it's an elastic collision, just like a tennis ball against a wall. Now, please remember that this is the model that we are building for this single atom. Now, in reality, I told you that this contains an s orbital when it's in the ground state, which contains 2 electrons. So, this has an internal structure. So, it's not a point particle. And furthermore, from the point of view of this atom, when it comes to this wall, the wall itself is made up of atoms which are jiggling. Now, when this atom comes and hits a vibrating atom inside the wall, it can get bounced off in any random direction. But we expect on average that it will behave like a tennis ball colliding elastically. In other words, we are making a model of this situation. We are going to assume that it behaves like a point particle, and as far as collisions with walls are concerned, it behaves like a tennis ball undergoing an elastic collision. This is a model. It's not reality. But we'll see how far we can take this model. Right? So when it comes and collides against this right side wall of the rectangular container, the x component of the velocity gets reversed. The y component of the velocity remains as it is, and the z component also remains as it is. Now, after it collides with this wall, it might go and collide with the roof. When it collides with the roof, once again, the z component of the velocity gets reversed, the x and y components do not change. And let's say it comes down and collides with the floor, and when it collides with the floor, the z component gets reversed again. The x and y do not change. Whatever it is, until it reaches this left side wall, the x component of the velocity remains as minus vx. So what is the time taken for it to get to the left side wall? The time taken is going to be the displacement divided by the constant velocity, Vx. Actually, the displacement is minus L if I take positive x direction to the right, and the velocity is minus Vx. So the time taken is L by Vx for it to hit here. I suppose you remember from river and boat problems and from projectile motion problems, when you want to find the time taken for a certain displacement in the x direction, you don't worry about what the velocities are in the y and z directions. They don't affect the problem. Displacement in the x direction divided by the x component of the velocity gives you the time. When it hits this wall, the x component gets reversed again and becomes plus Vx. Now the displacement is L again. So the total time for it to go and come back to the same wall is going to be 2L by Vx. Okay, what is the momentum delivered to this wall? Well, the initial momentum is mvx in the x direction. That is the only momentum that changes. mvy and mvz do not change. So original momentum was mvx. the final momentum is minus mvx in the x direction. So the change is final minus initial, that's equal to minus 2 mvx. That is the change in the momentum of the atom when it collides against the right side wall. So the momentum delivered to the wall is 2 mvx per collision. Now this is the time it takes between collisions. So how many collisions does it undergo against the right side wall per second? The answer is Vx by 2L. Let me explain that very quickly. If the time between successive collisions is 0.1 seconds, in 1 second it will undergo 10 collisions. So 1 divided by the time gives me the number of collisions per second. Each collision, it delivers a momentum of 2 mvx. So the total momentum delivered, the 2 cancels, is going to be mvx squared by L. Mvx squared by L is the momentum delivered per second. So this on average is the force exerted by this gas consisting of one single atom. Of course, it's not a steady force. Every time it collides, it imparts a momentum. But on average, this is the force, total momentum delivered per second. Let's now add n such atoms, where n is a large number. Let's say it's a small n, which is the number of moles multiplied by Avogadro number. What do you suppose these atoms are going to do? They're going to bounce against the walls, they're going to bounce against each other, they're going to exchange momentum, they're going to exchange energy with each other. But every time they collide against a wall, let's assume the collisions are elastic so that the speed doesn't change, only a certain component of the velocity gets reversed. For the moment, let's ignore collisions between the atoms. We'll come back to that later. In other words, we're going to now start treating the gas as though it consists of atoms which are independent of all the other atoms. Each atom moves merrily on its own way without colliding with any other atom. You see how we develop physics? You don't jump into a very complicated situation right away. You start with one atom, then you add n atoms, and then what do? You assume that they don't collide between each other, and then you bring in collisions. So steadily, this is how you develop a theory. Anyway, so let's get back to this. So if n atoms come and they're buzzing around, now each of the atoms has a different x component of the velocity. So I'll have to call it Vxi, Vx1, Vx2, Vx3, etc. So the total force exerted on the right side wall of this box is going to be m by L times sum over Vxi squared. Now what do we do with this? Now let me remind you that the average value of Vx squared, what does that mean? That means I go from atom to atom, take the square of the x component of the velocity, that is Vx1 squared plus Vx2 squared plus Vx3 squared, etc., and divide by the total number. That's going to be the average of the Vx squareds. So that's going to be summation Vxi squared by the total number n. That's exactly what I have here. So let me substitute this. So if I take this expression and take it there, I get the force exerted on the right side wall is going to be m by L times n times Vx squared. Vx squared, average. Now there is nothing special about the x direction. On average, for all these molecules, the average Vx squared, that is Vx squared average, is going to be the same as Vy squared average, is going to be the same as Vz squared average, because there's nothing special about the x direction. So this force, we can write it as m by L times n and multiplied by 1/3 of Vx squared average plus Vy squared average plus Vz squared average. But then this is equal to mn by 3L. What do we have here? Average Vx squared plus average Vy squared plus average Vz squared is going to be the average of Vx squared plus Vy squared plus Vz squared. But Vx squared plus Vy squared plus Vz squared is nothing but V squared. So V squared average. In other words, we end up with the square of the speed, the average of that. What's the meaning of that? The meaning of that is you take molecule 1, find the square of its speed, go to molecule 2. In this case, the molecule is nothing but an atom. Find the square of its speed, and so on and so forth, and add all of that and divide by the total number n. you get the average of the square of the speed. Now, if you look at the expression mv squared, does it ring a bell? Of course it does. So this is equal to n by 3L. I'm going to multiply it by half and divide by half. In other words, multiply by 2 and multiply by half. I get half m v squared average. I've taken m into the average because m is the same for all the atoms. This is nothing but the average kinetic energy of the molecules. So this can be written as 2n by 3L times the average kinetic energy. So we have one more step. This is the force. Remember that. What I'm going to do is find the pressure. So the pressure of the gas is going to be the force divided by the area of this wall. That's going to be equal to 2n by 3LA times the average kinetic energy. Now L times A, length of the box, times the area is nothing but the volume. So this is equal to 2n by 3V times the average kinetic energy. Take V that side, we get PV is equal to 2 by 3 n times the average kinetic energy. Now compare this with what we know from experiment done by Boyle and Charles and all those guys. We know that this is equal to nRT. Now remember, capital N is small n times Avogadro number. So if I put those together, we get PV is going to be equal to nRT, which is equal to 2 by 3 n Avogadro number times the average kinetic energy. So n cancels and we get, take Avogadro number that side and we define a new constant, the universal gas constant divided by the Avogadro number. We're going to call it K. This is called Boltzmann's constant. So this becomes, take 3 and 2 that side, we get the average kinetic energy is going to be 3 by 2 kT. So what does this tell us? This tells us that the temperature of a gas, up until now we only thought of it as the degree of hotness or degree of coldness or some such thing, and we used a thermometer to measure it. But now we find that the temperature of the gas, remember this is in Kelvin. Okay, this equation PV is equal to nRT, T is in Kelvin. So the temperature in Kelvin is actually proportional to the average kinetic energy of the atoms. So in the case of a monatomic gas, we are able to show, without taking into account collisions, remember that the temperature is nothing but a measure of the average kinetic energy of the atoms. What happens if I take collisions into account? Let's go to the next page. Now I hope you remember this about collisions. When two particles of the same mass collide in one dimension, that means it's a head-on collision. In the case of a head-on collision, if the collision is elastic and the masses are the same, they simply exchange velocities. So, our atom, which has a velocity in the x direction of Vx, let's say, it collides with another atom whose velocity in the x direction is Vx prime. What do you suppose will happen if it's a head-on collision? The atoms exchange velocities. So instead of this atom moving to the right at Vx, we end up with an identical atom moving to the right with an x component Vx. And this atom will push off in this direction with an x component Vx prime. But as far as this wall is concerned, an atom of the same mass will come and collide with it with the same x component Vx. In other words, it is as though this atom came and collided with this wall without having undergone a collision in between. In other words, if we assume that all the collisions are head-on and elastic, then all that happens is an exchange of velocities and the result does not change. What happens if the collisions are not head-on? Well, that's a more complicated situation which is outside our portions, but I assure you the results are going to be the same. So ultimately, we have derived that the average kinetic energy per atom is going to be 3 by 2 kT. This is the result of this simple exercise. What happens if it's a diatomic gas, if it's a polyatomic gas? We will talk about that in the next video. So for now, folks, goodbye. See you in the next video.